Okay, today's new topic is wind, and I'm starting off with local patterns of wind, and I asked that someone just throw a quick definition of wind at me. Wind is what?
A breeze.
A breeze?
It blows.
Blows meaning what?
Oh, it's a good pun.
How would you know if you walk outside and there's wind, how would you know?
Your hair is
Feel it.
Yeah.
You can feel it. What are you feeling?
Air.
Air doing what? Alright, air moving. I'll take that. So, wind you can just think of as moving air. So that begs the question, why does air move? Why doesn't it just stay right where it's at? Nope, doesn't have to do the moon. Is that right? It was heated, maybe. That could have something to do with it. The molecules want to move for some reason. What do you think, Henry? Nope, not specifically. I'll give you a hint. Here it is.
Balloons.
Okay. Yes, wind is because there are lots of balloons in here. If I release the pressure, if I release my fingers on the nozzle here, it's going to create wind. Why?
Pressure.
Pressure, yes. Where is the pressure higher? Inside the balloon. Why? Why is the pressure higher inside the balloon? It's being compacted. What's it being compacted by? The rubber. The rubber has some elasticity to it. I had to actually blow with a fair amount of force to force air into the balloon to push to stretch the rubber, and now it wants to stretch it back in the other direction. It wants to compact. So the pressure inside the balloon is higher because the rubber is pushing in upon it. So if I release my fingers, it will.
Why is it?
It will create wind. Yeah. So that's all, really. So what does that mean? It means air will move from an area of high pressure to an area of low pressure. Air will move from an area of high pressure to an area of low pressure. That's why we have wind. Wind is moving. Air molecules are trying to move from an area where there's higher pressure to an area where there's lower pressure. Some days in the morning, it's really cold in the hallway and warmer in the room. And what I will find is that I will open the door and air will move through the doorway because of that difference. So actually, I guess I just gave away part of my next question. If you think back to when we talked about barometric pressure a couple classes ago, and I described two things that could change the atmospheric pressure on a given day. Or put that up as two things that could change the barometric pressure on a particular day. What were those two things? What could make the barometer go higher or lower on a particular day?
Atmospheric pressure.
Yeah, well, it is atmospheric pressure. So what two things can change the atmospheric pressure?
Wind. Oh.
You want it?
Lots of evaporation.
Lots of evaporation, so humidity,
Yeah.
if that's what you meant. Yes, humidity is one of them. And temperature is the other one. I sort of gave that one away when I said sometimes I come in, it's really cold in the hall. So, warm air mass, cool air mass. Which one's going to be exerting a higher atmospheric pressure? Okay, it is cold. Because in a cold air mass, it's going to be more packed. The molecules will be more packed tight and more tightly packed together. So that air mass is going to be pushing down harder. So a cold air mass is going to be higher pressure than a warm air mass. The other question I could ask you now is humid air mass versus dry air mass. Which one is going to be exerting a higher pressure? Dry. And it goes back to which one's going to be heavier. The dry air mass is heavier because humid air masses, each one of those water molecules has a smaller weight than the air molecules that it has displaced. Where the water molecules are really light, I guess you could say. Okay, so the highest pressure air masses are going to be cool, dry air masses, and the lowest pressure air masses are going to be warm, humid air masses. So highest pressure air masses are cool and dry. And the lowest pressure air masses are warm and humid. Highest pressure air masses are cool and dry, lowest pressure air masses are warm and humid. So I'm going to draw a picture now and explain how that is going to help drive a local wind pattern in somewhere like here, like in South Portland where we live along the coast. So we've got some ground and we've got some ocean. I'll jog your memory of oceanography a little bit. What has a higher specific heat? Ground or water? Water. Okay, I heard at least 3 people say water. Those people were correct. Water has a higher specific heat. So let's say in the morning the sun comes up and it begins to beat down upon the land and the water. Which one's going to heat up faster? The ground or the land will heat up faster. The water heats up slower because it has a high specific heat. Having a high specific heat means it takes a lot of heat to change the temperature. So what you've got is you've got a cooler air mass here sitting over the ocean. So the cooler air is the higher pressure. This might help. If you feel like it helps your understanding, then sure. So you have the cooler, higher pressure air mass sitting over the ocean because the ocean heats up slowly and the air above the ocean is going to be affected by the temperature of the water. Over the land, you're going to have a warmer air mass. The land is heating up quickly, thus the air above it's going to be able to heat up quickly, so this is going to be a lower pressure. Well, that's one reason. And which way is the wind usually blowing when you're near the coast? Sorry? Say again. In from the water. Yeah, you usually have, or you often have a sea breeze along the coast. What a sea breeze is the cooler, higher pressure air moving into the area of the warmer, low pressure air. That's why along the coast we usually have a sea breeze, and along the coast it usually doesn't get as warm as inland. So here's your sea breeze, where your cooler, higher pressure air is moving from the area of high pressure to low pressure. And looking at this lava lamp right here might give you a clue as to what's going to happen to that warmer, lower pressure air that's sitting over the land. It's going to warm up, become less dense, and rise. Okay? So the warmer, low pressure air is then going to begin to rise. If it's humid, you might get cloud formation on that day as it rises farther up into the air. And then at some point, you're going to have that air cooling off and sinking back down, and it's basically going to form a kind of a, what have I just drawn there? A big circle. I heard the word, you said it. I've drawn a big convection cell. So this is basically showing you a big convection cell. Cooler, high pressure air is going to push onto the land where the warmer, low pressure air is. That air is going to rise. You're going to have a big convection cell going on. So that's one of the reasons for the sea breeze along the coast. Now, I'll briefly talk about global weather patterns, global convection patterns, and then we'll go outside and do our little demonstration to show the Coriolis effect. So first, here, let me draw a globe. Here's the Earth. Equator. right? Where on the Earth does the sun strike most directly? The equator, so it's the warmest there. What that means is that the air around the equator is going to be warm and it's going to be rising. So warm, rising air at the equator. It's going to spread and head away from the equator and spread and spread and get cooler and cooler, and then ultimately it's going to start to sink. Then it's going to spread back across the Earth's surface like this.
So it's just one big.
Well, this is an idealized version of global convection. If the Earth was either entirely land or entirely water, and it did not rotate, this is exactly what would happen. This is called the one-cell model of global wind patterns. And the one cell, this would extend all the way around the Earth in a three-dimensional sense. So you have one big convection cell in the northern hemisphere, you'd have one big convection cell in the southern hemisphere, and this one-cell model would work if, once again, you had all land or all ocean and the Earth didn't rotate. And why those two things are important, I'll explain later. So, if no rotation, if all land or all water. This one's easier to explain. If the if the Earth was all land or all water, then the heating everywhere would be about the same, because the ground would heat up at the same rate. But because we have part ocean and part water, some heat up faster than others, so we have a difference in temperature. And also, air masses over the water tend to be more humid because there's more evaporation. So you have the fact that we have land and water fouls up the humidity and the temperature of the air and makes it different everywhere. And that's one of the reasons it's so difficult to predict the weather, is because we have these wild differences in temperature and these wild differences in humidity due to the fact that we have both land and ocean. So that's one of the reasons that this one-cell model doesn't work perfectly. The other reason is because the Earth rotates, and that is much more complicated to try to explain. So what we're going to do now is go outside for maybe about 10 minutes and do a little demonstration that hopefully will explain why. Now I'm going to attempt to explain how that actually relates to this convection model and why it doesn't work. Let's imagine me, I was running along the equator in this direction. Okay? Well, it would be. And the line of people that I was throwing to was standing up here on, if it was Portland, Maine, it would be about 42 degrees north latitude or something. So I'm throwing it this way. Now, well actually, I think as where it pertains to a throw, this is not exactly applicable. However, if you were to take like a piece of artillery or want to fire a missile or fly an airplane from here to here, this definitely would affect you and you'd have to compensate for it. When you are standing on the equator of the Earth, just standing in one spot, you move all the way around the Earth one time every 24 hours. Does that sound reasonable? Earth rotates once every 24 hours, you come back to the same spot. The distance around the Earth, if you measure it, is a little more than 24,000 miles. So if you're standing on the equator of the Earth, you're actually moving about 1,000 miles an hour in the rotational direction of the Earth.
You saying I'm moving 1,000 miles an hour right now?
Yes. Well, we're not on the equator.
Fast.
We're not on the equator. Yes.
Okay, this is it's like kind of related to this, but okay. Say if you were in the air, like on a plane or floating or something, like hovering, like a certain amount of feet, would you like for
Spit it out.
24 hours
Would the Earth rotate underneath you? No. The reason it wouldn't is because the air mass is moving too. for you to stay in one spot, the air would have to be whistling past you at 1,000 miles an hour, and you'd have to have some way of fighting against the air's
What if
rotation.
you do that?
Well, yeah, sure. If you take an airplane, now this is going to bake your noodle a little bit. If you take an airplane, and your noodle meaning your brain, if you are flying west at 1,000 miles an hour, you're not actually, you can think of it as saying you're not actually moving in your plane. Your plane is staying in one spot while the Earth rotates 1,000 miles an hour in the other direction. You will end up 1,000 miles an hour west of where you were, but only because you're staying stationary while the Earth moves under you.
So it's essentially like your plane just got up off the ground, stayed there,
Yeah.
and the Earth just
And
went like
basically,
this.
it's firing its engines just to keep the air from pushing it that way.
Is that true?
Well, you can think of it either way. From the frame of reference of somebody in space, that's exactly what's happening. If we were looking down the Earth and we saw an airplane that's flying this way, but we're just looking at the Earth, it's flying 1,000 miles an hour that way, and the Earth is turning 1,000 miles this way. The plane to us is not going to appear to move. It's going to seem like the plane's staying in the same place and the Earth's turning under it.
What if it's going the other way?
This
That doesn't
way?
look like it's moving.
Well, it would just appear like it was sort of, yes, it would appear as though it was moving.
So that's like when a bird flies with the wind, it just has its wings out, just glides, but if it's flying against the wind, it has to flap really hard just to...
Yeah, it's all dependent on your frame of reference, though. It depends on whether you're looking at it from an outsider's perspective. Now, from the perspective of somebody standing under the plane on the ground, yeah, it would appear as though the plane was flying west at 1,000 miles an hour. But from the point of view of someone in space, it would appear as if it was just sitting. So,
What would happen if the plane was going like 1,020 miles an hour? Would then it look like it's moving?
1,000 miles, 20 that way?
Yeah.
Yes, the plane would be moving 20 miles an hour that way, while the Earth rotated 1,000 miles an hour that way, from the perspective of someone like in space. The reason I brought this up is because, well, let's imagine up here. In 24 hours, you also make it all the way around the Earth, but because this circle is not as big, you're not moving as fast. Let's say you're only moving 750 miles an hour. In this rotational direction. So if I throw the ball from here to here, I'm going to not only have a north component to my throw, there's going to be an east component that I'm not even thinking about at about 1,000 miles an hour. And I'm throwing it from an area where that's moving faster to the east to an area where that's moving slower to the east. So what's eventually going to happen is that just like when I was running this way and throwing sideways and the ball was ending up going to the person that was a couple steps in the direction I was going, something flying away from the equator, whether it be an airplane or a projectile or what, or an air mass moving away from the equator, that thing will be deflected off to the east, like that. Because the initial velocity in the east direction, because of the way that the Earth is turning. Now, let's imagine for a moment that we're out duck hunting. So we're sitting in our, I don't know, wherever you sit when you're duck hunting, and you see a duck, and it's flying this way across your field of view, and you're aiming this way. So what's going to happen if you fire the moment that the duck crosses your plane of
You're
view?
behind it.
You're gonna miss behind it, and then the little dog will pop up out of the bushes and laugh at you. Like, everyone's played Duck Hunt on the old Nintendo. So, by the same token, if you left south from up here, and you were aiming at this spot on the equator, by the time you got there, the Earth would have rotated past, and you would end up west of where you were aiming. So if you traced your path across the Earth's surface, it would look like this. And now, you're not actually going a curved path. The thing isn't actually going a curved path. It's going a straight path. But if you traced it across the Earth's surface, it would appear to curve. Let's see, if the Earth was not turning, it would go a straight path. If the Earth is turning, it's still going to go a straight path, but that straight path is now going to take it west of where it otherwise would have been. Because the Earth turned.
Does that mean that if you're a pilot, it's really hard to navigate where you're going? 'Cause if you're
You
doing
have to
this-
compensate for this if you're flying north or south long distances, because if you're flying this way, away from the equator, yes, if you don't compensate for this, you will end up to the east of where you were aiming, and vice versa. Because the Earth turning, and the different velocities of the different latitudes is going to be problematic for you. This effect has this. It works the same in the southern hemisphere. You're still being deflected off to the east in the southern hemisphere, like so, because you still are moving faster in that direction. And if you're moving back towards the equator in the southern hemisphere, it's still going to end up looking like that if you trace your path across the Earth's surface. That is called the Coriolis effect. I've just illustrated what's called the Coriolis effect.
Is that gonna be a test? Do I have to draw that?
Well, if it helps you understand the Coriolis effect, then perhaps it would be a good idea to draw it.
Is that gonna be a test?
Maybe, maybe not. So, it could be, I'll put it that way. If you look at the way these, what direction is that, rotationally? Clockwise, how about this? Counterclockwise. Remember your gyres?
Same thing as the
Remember your
tide.
gyres moving clockwise in the northern hemisphere and counterclockwise in the southern hemisphere? That's why. Because your wind patterns do that, and your wind patterns, are driving surface currents. That's why you're having clockwise movement of gyres in the northern hemisphere and counterclockwise movement in the southern hemisphere. But how that affects your global convection cell, now it doesn't work anymore. Because what happens is an air mass starts off moving to the north, but long before it gets there, it bends to the east, and it cools off and sinks right away before it has a chance to get all the way up here to the poles. So your convection cells don't look like this one big happy convection cell. It looks more like, well, okay, this air mass is going north, but it's bending to the east, so it's going to, the air is going to get cooler and sink way up here before it gets any farther. And so forth. You're going to have, instead of one cell, you're going to have, well, the best model that we have, which is still not a perfect model, has 3 cells of global convection. And actually I can pull up a photograph for you real quick. I think I'm still connected.